Hi, my student. Today we will learn Chapter 7, Computational Paradigm. In this chapter, we will learn about processor organization, register organization, instruction cycle, and data flow, instruction pipelining. Processor organization, they have three components, which is ALU, Arithmetic Logic Unit, perform calculation and comparison, which is data change, CU, Control Unit, perform fetch and execute cycle. The function CU is move data to and from CPU register and other hardware component. No change in data. Accesses program instruction and issue command to the ALU subpart. Memory Management Unit supervise fetching instruction and data. Input-output interface, sometimes combined with Memory Management Unit as bus interface unit. Register, example, program counter, PC, or instruction pointer, determine next instruction for execution. This example of block diagram, we have CPU, input-output interface, ALU, control unit, and memory. Here you can see any input from the keyboard, for example, or output, which is printer or camera. Any input, we go to the control unit for the process and we'll put in the memory track. Okay, this is sample for the system bus, how the data processing. LU does the computational of processing the data. Control unit control the movement of data and instruction in and out of the processor and operation of ALU. Register set of storage location. CPU, things that it must do. Fetch instruction. The processor read an instruction from memory, register, cache, memory. Interpret instruction. The instruction is decoded to determine what action is required. Fetch data. The execution of an instruction may require reading data from memory or input-output module. Process data. The execution of an instruction may require performing some arithmetic or logical operation on data. When right, the result of an execution may require writing data to memory or an input-output module. Hence, a small amount of internal memory, called the register, is needed by the CPU to fulfill this requirement. You must remember location of last instruction, store instruction, temporary data while instruction is being run. Instruction cycle include the following stage. First, read the instruction from memory into the processor, decode or execute, interpret the opcode and perform the indicated operation, interrupt. The interrupt are enable and interrupt as a cure, save the current process state and service. Indirect, require additional memory access. Example, indirect addressing. This example of instruction cycle. Instruction fetch the data and will go to the operation decode. This file will decode in binary 01. Operand address, if they have a calculation, they will do the operation. And then you go to operand fetch and go to data operation and move to operand address calculation. Then you will store the result and interrupt a check if any others job. And If no interrupt, they will return for the string of the vector and instruction complete and fetch need instruction. You must remember, in this cycle, they will have a queue or scheduling for each instruction. For example, first in, first out instruction. Data flow, fetch cycle. During the fetch cycle, an instruction is read from memory. The PC contains the address of the next instruction to be fetched. This address is moved to MAR and placed on the address bus. The control unit requests a memory read and result is placed on the data bus and copy into MBR and then moved to the IR. The PC is incremented by 1 preparatory for the net fetch. Data flow, indirect cycle. Once the fetch cycle is over, the control unit examines the content of the IR to determine if it contains an operand specifier using indirect addressing. If so, an indirect cycle is performed. The rightmost and bit of the MBR, which contain the address reference, are transferred to the MAR. Then the control unit requests a memory read to get the desired address of the operand into the MBR. Data flow, decode or execute cycle. The execute cycle depends on the various machine instruction is in the IR. This cycle may involve transferring data among register, read or write from memory, or input-output and or the invocation of the ALU. Data flow. The content of the PC are transferred to the MBR to be written into memory. The special memory location reserved for this purpose is loaded into MAR from the control unit. For example, it might be stack pointer. The PC is loaded with the address of the interrupt routing. As a result, the next instruction cycle will begin by fetching the inappropriate instruction. Data flow, interrupt cycle. The content of PC are transferred to MBR, rewritten. The special memory location reserved for the purpose is loaded into MAR from control unit. The PC is loaded with the address of the interrupt routine. As a result, the next instruction cycle will begin by fetching the appropriate instruction. Here the sample from the PC to memory and then go to control unit from MAR to the main memory. And then it will return back to the PC. Instruction pipelining. It is a technique used in a design of computer to increase the instruction throughput. The pipelining does not reduce the time to complete an instruction, but increase instruction throughput by performing multiple operations in parallel. Instruction pipelining used to speed up processor execution. Pipelining involves breaking up the instruction cycle into a number of separate stages that occur in sequence. For example, fetch instruction, decode instruction, determine operand address, fetch operand. Analogy, manufacturing assembly line. By laying the production process out the assembly line, product at various stages can be worked on simultaneously. This process is also referred to as pipelining because, as in pipeline, new input are accepted at one end before previous accepted input appear as output at the other end. Pipeline strategy. Example, subdiving instruction, process into two stages, fetch instruction and execute instruction. During the execution of an instruction, there are times when memory is not being accessed. This time could be used to fetch a next instruction in parallel with the execution of current one. The first stage fetch an instruction and buffer it. When the second stage is free, the first stage pass the buffered instruction. While the second stage is executing the instruction, the first stage take advantage of any unused memory cycle to fetch and buffer the next instruction. This is called instruction prefetch or fetch overlap. Pipelining strategy. Now, pipelining requires register to store data between stages. This process will speed up instruction execution. If the fetch and execution stage of equal duration, the instruction cycle time will be half. Pipeline decomposition. Pipelining can severely cut the time taken, but the instruction execution process do not necessarily take an equal amount of time. Time taken to execute generally longer than fetch, and this made it much harder to synchronize the various stages of the different instructions. Also, some instructions may be dependent on the result of other earlier instructions. This can arise when data produced earlier need to be used, when conditional branch based on previous outcome is used. As a solution, breaking the instruction execution cycle into stages that are more likely to be an equal duration. For example, the diagram below shows how the cycle can be broken down into 6 stages rather than 3. Fetch instruction and the decode instruction, calculate operand, and execute fetch operand, execute instruction, and write operand. Okay, continue. Pipeline contains several stages. Fetch instruction, read the next expected instruction into buffer. Decode instruction, determine the opcode and the operand specifier. Calculate operand, calculate the effective address of each source operand. This may involve displacement, register indirect, or other form of address calculation. Fetch operand, fetch each operand from memory operand in register need to be fetched. Execute instruction, perform the indicated operand and store the result, if any, in a specific destination operand action. Write operand, store the result in memory. This figure shows the 6-stage pipeline can reduce the execution time for 9 instructions from 54 time unit to 14 unit. Assumption. All instructions are equal duration. Each instruction goes through all 6 stages of pipeline. All of the stages can be performed in parallel. There are no memory conflict. For example, fetch instruction, fetch output still involve memory access. The diagram implies that all these access can occur simultaneously. Most memory systems will not permit that. However, the desired value may be in cache. Thus, most of the time, memory conflict will not slow down the pipeline. Advantage pipelining. The cycle time of processor is reduced by increasing the instruction throughput. Pipelining does not reduce the time it takes to complete an instruction. Instead, it increases the number of instructions that can be processed simultaneously and reduce the delay between complete instructions. The more pipeline stages a processor has, the more instructions it can process, and less of a delay there is between complete instructions. If pipelining is used, the CPU arithmetic logic unit can be designed faster. Disadvantage of pipelining. The design of non-pipelining processors simple and cheaper to manufacture. Non-pipelining processor execute only single instruction at a time. In pipeline processor, insertion of flip-flop between module increase the instruction latency compared to a non-pipeline processor. Many designs include pipeline as long as 7, 10, 20, 31, and even more stages. A disadvantage of long pipelining is when program branch, the entire pipeline must be flushed or cleared. The higher throughput of pipeline falls short when execute code contain many branches. The processor cannot know in advance where to read the next instruction and must wait for the branch instruction to finish, leaving the pipeline behind it empty. When programmer or compiler write assembly code, they generally assume that each instruction is executed before the next instruction is being executed. When this assumption is not validated by pipelining, it causes a program to behave incorrectly. Thus, it's known as a hazard. Various techniques for resolving hazard or working around, such as forwarding and delaying by inserting a stall or waste clock cycle, exist. Thank you, everyone.